We're continuing with the second video of this set. In the first video, we covered the motivation, the definition of function spaces, and the definition of metric spaces with plenty of examples. And now let's get on to vector spaces and normed vector spaces. Now, vector space is simply a space where we define operations which are addition of vectors and multiplication by scalars. And these operations of addition and multiplication must satisfy the following 8 properties. Some of you may already be familiar with these properties because you're used to dealing with finite dimensional, n-dimensional vectors, n-dimensional real vectors like those in Rn. But as we'll see that there are many other kinds of vectors which also form a vector space. And that's why it's important to keep these properties in mind, maybe at least at the back of your mind. You don't have to remember all of them. The first one is just associativity of addition. The second one is commutativity of addition. The third one says that there must exist a zero vector such that v plus 0 is v for all vectors v in your space. Again, for all vectors v, there exists an additive inverse called minus v such that v plus minus v is 0. The next one talks about how multiplication of scalars works, and so if you first multiply the scalar to the vector followed by multiplication with another scalar, you get exactly the same quantity as if you multiplied the two scalars together and then multiplied by the vector. So multiplication must satisfy these properties. Then there must exist a scalar which we call 1 such that 1 times v just equals v for every vector v in your space. And the last two are about the distribution of multiplication, the first time over addition of vectors and the second time over addition of the scalars. Again, these properties are fairly natural if you're already used to thinking about vectors as finite dimensional Euclidean, real vectors. But there are other examples of vector spaces that one must keep in mind. Here's one that you might not be familiar with. It's called little l1 or small l1 of R, and it's the set of all sequences. And a sequence A is basically A1, A2, and so on. And it's possible. It's an infinite sequence. And L1 of R is the set of all sequences such that the summation of AI is finite, and of course I goes over the entire range, which is infinite. So these are what are called sequences, and if they're L1 additive, that is the sum of their L1 norm is basically finite, then any such sequence is in the set L1R, and this set L1R is actually a vector space. We've already seen L2R in the previous video. I'll remind you what it is. It's a set of all functions such that when you integrate from minus infinity to infinity, f of x squared dx, that this integral is finite. And the set of all such functions is also a vector space. And lastly, this is the set of m cross n matrices. So clearly, even though you're used to thinking about only this case, one should keep in mind that it's much rich. Vector space, the study of vector spaces encompasses much richer objects. Let's move on to the concept of a normed vector space. A normed vector space is nothing but a pair f and a function where f is a vector space and this function is a norm. Now I call it a function because it actually does act on elements of the space and it gives you real values, positive, non-negative real values. But this is a tedious notation, and so we use this notation. But basically it is a real valued function, a non-negative real valued function. And a norm is any function that satisfies the following properties. For every f in your space, as I said earlier, it must be non-negative, and also it must be 0 if and only if f is equal to 0. As before, if you drop this assumption, from a metric we got a semi-metric, and over here from a norm we get a semi-norm. The second one is just like a triangle inequality or a sub-additivity of norms. And the last one says that if I multiply by a scalar, then the effect of the norm is just multiplied by the norm of the absolute value of that scalar. So again, if you're used to thinking about f as being a usual finite dimensional vector space, then you might already be familiar with some of these properties, or they might seem natural to you. But f could be much more general. So here are some examples of vector spaces. If you're dealing with finite dimensional vectors, the L1 norm is just defined as the sum from I is equal to 1 to n of mod xi. Similarly, the L2 norm would just be the sum the the square root of the sum from I is equal to 1 to n of xi squared. And lastly, the infinity norm is just uh, the max overall I of mod xi. So for the same underlying space Rn, we have now, we can define three different norms. But actually, the underlying space need not be Rn. It could be the set of all sequences like we just saw. And the L1 norm of any point in your space is just defined as the sum from I is equal to 1 to infinity of mod ai. So if A is your sequence in L1, then its L1 norm is just given in this fairly natural fashion. Similarly, if f is a function in L2, that is, it is square integrable, then its L2 norm is just given again fairly naturally by the square root of the integral from minus infinity to infinity f of x squared dx. And lastly, if I'm dealing with matrices, then the infinity norm of the matrix is the largest element, just like the infinity norm for a vector, it's the largest element of the matrix. Now again, I can define the L2 norm and L1 norm and so on for this matrix. And basically the point is you can pretty much have a rich variety of spaces and a vast variety of norms. The last crucial point that I want to mention is that a norm implies a distance metric. What do I mean by that? If I give you a normed vector space f and a norm, I've given this to you, I fix this, then I can define a distance rho between points f and g in my space in the following fashion. I define rho of f comma g as the norm of f minus g. Right? So rho has not been defined. I've not been given a metric space. I'm given a normed vector space, but a normed vector space automatically defines a metric in the following fashion. Now, is this, you might ask, is this really a valid distance metric? In the last tutorial, we saw what the properties of a distance metric were, so we can verify that these hold. Because this is a norm, we know that the norm of f minus g has to be positive, which basically implies that rho of f comma g is always positive. We know that the norm is 0 if and only if the element is 0, and this immediately implies that rho of f comma g is 0 if and only if f is equal to g. Again, the norm of f minus g is the norm of g minus f. Here you can take the constant minus 1 in the last property I introduced to verify that this really holds true for norms. And again, this implies that rho of fg is rho of gf. And using subadditivity of norms, we can see that the norm of f minus h, you can write that as f minus g plus g minus h. And that is less than equal to the norm of f minus g plus the norm of g minus h. And this is exactly the triangle inequality for the metric. And so what we can see is for the same underlying space f, we can define different norms, and each of those norms gives rise to its own metric. So if this norm was the L1 norm, then the appropriate metric would be the L1 distance between f and g. If this was some other L2 norm, then this would be the L2 distance between f and g, and it could just be any other norm which would define its own distance metric. This is quite a crucial property. That's all I wanted to say now about normed vector spaces. Let's get back to inner product spaces, the most important part of this tutorial, in the next video.